Okay, this next circuit I'm going to talk about is an integrator. It's a little bit more complicated than some of the other circuits I've discussed so far. So what have we got here? Well, this has negative feedback once again between our output voltage and our inverting input. That makes it negative. But there's a capacitor over here. So what is this doing? Well, and the input is basically coming through a resistor into this leg. Meanwhile, the positive is tied to ground. So what this is doing is basically any current that's the result of a difference in the voltage here and the voltage here is going to flow through the capacitor and the resistor. That means that a current that goes across this is going to change the potential here. And essentially what this point wants to get at is it would like to basically be one, the output is going to adjust so that this is as close to ground as possible. But two, the potential across here wants to remain fixed. Basically, current runs until such point as current can run no more. The capacitor kind of hits a fixed value. So what does that work out to be? Well, for figuring all this out, you got to use your calculus. What you're going to find is that the output voltage should be equal to the opposite of the integral of the input voltage divided by RC over time. So this circuit basically integrates your voltage. So it's a little bit more complicated than some of the other circuits we've looked at, a little more complicated to analyze. But if you want to spend some time looking through it and looking up some resources better than this video, you can find it. So what do I have set up here? Well, I've got the integrator circuit with a 10 mega ohm resistor, a 0.1 microfarad capacitor, and I'm reading the output voltage onto my meter there. And I've also got an input voltage hooked up to my potentiometer. Now it's really difficult to basically get this set up so that it stays around zero. This really wants to integrate small voltage changes and bring them up to, positive or negative saturation. Right now it's at positive saturation because I have a negative input voltage going in. If I switch that to positive, what we see is I'm not changing the voltage anymore, but the capacitor is basically charging up. And so a positive input voltage caused this slow rise, a linear rise actually, or a linear fall, I should say, because of this negative sign here, because this is the inverting input. A positive static voltage caused a linear fall with a slope that's related to the voltage in and the RC. And if we switch that back to a negative number, I do a quick switch, and we'll see that the voltage drops down linearly. Now, if you have or it goes up linearly. If you have an oscilloscope, you can look at see if this is linear. I can't really convince you of that other than to watch the meter. I now put it at a fairly small voltage, but it tends to integrate fairly quickly. So this can be useful for smoothing out step functions in voltage if your voltage is changing, or if you want to see, for example, turning from an off to an on and then to an off again. You want to limit the time, perhaps produce a pulse. You can wire this in so that basically you can put a time component onto that pulse, figure out how long based on the linear rise, in the, or linear fall in the voltage, how long the voltage has been on. You can also use this to do calculations. This can actually be turned into an analog computer. If you have, several of these, you can solve differential equations using circuits, which can be pretty interesting. But we're going to use this in our fading hat circuit. You remember that fading hat? It's been a while. To basically smooth out the pulses of our oscillator. So instead of going, positive voltage, negative voltage, positive voltage, negative voltage, this is going to be the basis of turning that oscillation into a slow rise and fall. Okay, so for this next circuit, we're getting to something fun and interesting. We're going to be combining positive and negative feedback in a single op-amp to produce oscillation. So that's going to start blinking some lights. So what do we have here? We have the relaxation oscillator. And what's this doing? Well, we can kind of figure it out by analyzing each part of the circuit separately. So let's take a look at this bottom part of the circuit. This is positive feedback, 2 resistors. Well, it looks like a Schmitt trigger. A Schmitt trigger with the input set to ground. I've even made it easy by setting these 2 resistors to the same value, R. So what is this going to do? Well, this is going to set a potential here at which triggering would occur to be 1/2 the output voltage. So that's just a pretty straightforward divider. If this other input goes below 1/2 the output voltage, and the output voltage is high, the output voltage will switch down to low. And if this goes above, or actually if it goes below 1/2 the input voltage, since this is the inverting endpoint, this will switch to high. And if it goes above 1/2 the input voltage and the input voltage is low, this is going to switch back to low. So I may have just screwed that up, but in any case, this side is just a Schmitt trigger. We'll get to a diagram explaining how everything works. What about this side here? Well, this side, we haven't seen this exact configuration before. Let's try to figure it out. So we've got a capacitor here, a resistor here. We know current isn't going to go in here, so current's going to flow across this RC circuit. So that tells you a little something that says this is going to have some sort of time scale on which it operates. And that time scale is going to be this, which I've called the RT, which is the timing resistor, times the capacitor. So it's going to do something along that scale. Well, let's figure out what it does. One end of the capacitor is tied to ground, and we know that a capacitor doesn't quickly switch its voltage, right? You change the voltage, say here, and the voltage here is going to stay fixed, at least instantaneously. You need to have a current go into a capacitor in order to change the potential across it. So that tells us this potential is not going to change instantaneously. It's going to be tied to a certain level above or below ground by this capacitor. So the potential here, which I've labeled VA, is going to vary slowly. So let's imagine what happens. Let's assume this output is -5 volts. And let's say this potential starts at 0 across here. Well, we're going to have a current flowing across this resistor, since the potential here would be 0 and the potential here is -5, and that current is going to result in a growing potential across the capacitor. That current will keep going until this point reaches -5, all things being equal. So that means this input is going to slowly vary. So let's tie both ends together. What are we going to see? And I've got that kind of sketched out in this diagram. We can assume that the output is going to have a range from the positive source voltage down to negative source voltage, which in our circuits have been +5 volts and -5 volts. And let's assume when we turn it on, some instability is going to exist, and that's going to push it down to push the output down to -5 volts. So here the solid line shows the output. If it's at -5 volts, and we'll start the potential at VA up here, which is the dotted line, we'll assume it starts at 0. Well, this the current flowing through here is going to start pulling down the potential here as a charge builds up on the capacitor. So we're going to have a slowly varying, slowly descending voltage here until it hits the tripping voltage. This is at -5. This will be kind of -2.5 here. When this gets down to -2.5, below -2.5, all of a sudden the Schmitt trigger is going to activate, and this is going to jump up to 5 volts. So what that looks like here, so we've got dropping, get down to -2.5 volts. This voltage suddenly increases. This voltage can't react quickly because it's tied to its current position by the capacitor, but the current direction is going to reverse. The capacitor is going to discharge and then charge in the reverse polarity. So this means don't use an electrolytic capacitor until it hits plus 0.5. And then the switch is going to activate again. You've got that zone of hysteresis going on here that we know of from the Schmitt trigger video. And the output's going to drop down to -5. And then the whole process repeats again. So we're going to end up, the output's going to be a square wave oscillating on a time scale approximately or related to or proportional to the resistance of the timing resistor times the capacitor value. So I've set this up on my breadboard. I've run it through an LED so we can watch the square wave occurring. When the output is positive, the light turns on, and when the output drops down to the negative side, the LED turns off. And so what do I have here? Well, this resistor is just connected to the LED, so that's not part of our circuit. But what I have are two 10 kilo ohm resistors. Those are making the Schmitt trigger. So one is going from output to the one that's behind the LED is going from the output to the positive or the non-inverting input of the op amp. The other one's going from the non-inverting input to ground. And ground is connected up with this brown wire in this case. And then we also have this 10 mega ohm resistor going from the output to the inverting input, and then this disc capacitor, which goes from the inverting input over to ground. So those are the active components in this relaxation oscillator. So the capacitor is I think 0.1 microfarads. I just kept, I had this capacitor laying around, I just kept raising the resistance I used there until I got something that blinked on kind of a nice time scale that was easily visible. You'll probably need a pretty large resistor because since this capacitor is charging and discharging in two polarities, you can't use an electrolytic capacitor there, or you shouldn't use one. You're going to have to use a conventional capacitor, and those are limited. And I only had a couple different capacitors around when I was putting this circuit together, so the resistors had a far greater value. You don't have to worry too much about the current going through here. The currents are very small, so that's not going to produce much heat. Okay, now we're ready for the big reveal. This is the triangle wave generator, and this is the circuit I used in my fading hat for Burning Man. So we can actually understand this circuit pretty easily. It's just a combination of a Schmitt trigger and an integrator. And there's feedback within the integrator, as we've seen before, feedback within the Schmitt trigger, but there's also feedback from the end of the integrator to the input of the Schmitt trigger. So how does this work? Well, for the Schmidt trigger, basically we're going to have oscillation coming out. This is going to slowly rise and fall. That's what we want. So coming in, we have a slowly rising and falling signal. That's going to result in a square wave here. You know, you rise past the threshold, this will invert, go to positive, and then if you go down below the threshold, this will invert again and go negative. So we're relying on the hysteresis effect of the Schmidt trigger to basically create a square wave. So we're going to have a square wave here. That square wave goes into the integrator and it basically gets turned into triangle waves. You know, integration of a step function is a line, so a rising line for positive voltage and a falling line for negative. So out here we get a triangle wave. And so here it is. We'll assume we start at 0 and start rising. It could start falling or rising. You really can't predict what it's going to do. But it rises up, then starts to fall, and then rises up again. So what voltages does it achieve? Well, those voltages depend on the trigger points. And the trigger points are given by these two resistors. It'll actually be R1 over R2 times Vs in the positive and negative side. You should have R1 less than R2, probably significantly less, or else your op-amp is not going to be able to push up to these trigger points. What about the time scale for the wave? Well, the time scale is given by this resistor and this capacitor. They form an RC circuit. Time scale will be approximately equal to R3 times C. So I'm using values I've already used. R1 is 47 kiloohms, R2 is 100 kiloohms, R3 is 10 megaohms, and the capacitor is 0.1 microfarads. So let's take a look at the circuit. So you can see I've wired it up with two LEDs that are fading on and off. I'll tell you why I use two LEDs in a minute. I've got on the top part the integrator. So I've got the capacitor over here connecting the output to the inverting input. I've got a resistor, the 10 megohm resistor, actually going from the inverting input to the output of the lower op amp on this dual op amp chip. So that's just connected right across there. And on the lower part I have the Schmidt trigger. So the Schmidt trigger, it has a resistor, this one in here, connecting the output to the positive input. That's the 10 kiloohm. And on this side I have the 47 kiloohm resistor, which is getting feedback along this brown wire from the output down through into the non-inverting input. And then I have the green wire connecting the inverting input on the Schmidt trigger to ground, and the gray wire connecting the non-inverting input of the integrator to ground. So we can see I've wired the output of the integrator, the top op amp, to these two resistors, or two LEDs, and then it goes out through this resistor, and it actually is connected up to the minus 5 volt source on the top. So let's take a look at what the voltage is doing. We can see the voltage kind of varying up to between about -2 and +2 volts. This meter is sort of not measuring it. I mean, if we had an oscilloscope, which may be fun to invest in, you'd see the linear rise and fall. Part of the reason why I don't use an oscilloscope is you don't need to invest in an oscilloscope to get started in electronics. You might look at EEV blog or some of these other blogs and think, how am I going to get the money for all that equipment? Well, you get it slowly and over time. So in this case, just starting with a multimeter, subcomponents, and a building. Well, speaking of cheap components, my recording kind of crapped out there for a second. What I was saying is you can kind of start on a budget and build up circuits with a minimum of investment. Anyway, why do I have two LEDs there instead of one? Well, my positive voltage is going up to about +2, +2.5, and I'm dropping down to -5 volts across the LEDs and resistor, and so I wanted more voltage drop in order to have these LEDs turn completely off. So that's why I put in two there. You can adjust things so you get one LED turning off completely. It's you can finesse the circuit as you want. Now, one of the things that I said I would talk about, and I'm kind of leaving it as an exercise for you, is this op amp only produces maybe about 60 milliamps, maybe 40 to 60 milliamps. That's enough to drive these two LEDs. So what if you wanted to put on a bunch? In my hat I had 8 LEDs. So how do you do that? Well, it turns out you can use a transistor and set it up in this configuration. You have the output from the op amp and doing whatever it's doing over here, and you feed it through a transistor such that it goes into the base. The collector is connected to positive voltage, and here at your emitter, you're going to get the output of the voltage output of the op amp minus 0.7 volts. There'll be a 0.7 volt drop here approximately. And you can hook this up to the load. And so this maybe only can provide 40 milliamps, but through this transistor you can provide a lot more. Typically up to 100 times the current coming out here. If that's not enough, you can use a Darlington, which is basically 2 transistors. Make sure you look at the rating of your transistor. You don't want to try to put 2 amps through a transistor that can't handle it, or else you get the blue smoke and everything smells kind of bad. The other thing you might be thinking is, I don't want it to drop 0.7 volts here. I need that 0.7 volts. Well, you don't have to take feedback from here. You take your feedback from this point, right at the end of the transistor, and you can make this voltage be what you want it to be, up to the limitation of what the maximum voltage this op amp can put out, minus 0.7 volts. So you'll have a constrained range, but you can still take feedback from this point. So if you need to provide more power from your op amps, you can use a transistor. I'm not going to wire this up, but that's how I power more LEDs in my hat with a pretty cheap transistor. So hopefully I've shown you the usefulness of op amps. You're going to go out and buy an op amp now. You might look it up and say, oh, I'll buy one, and then you'll realize the shipping cost is much more than the op amp itself, and you'll say, well, I should buy 10, and then you'll realize it's probably about equivalent, and you've got a discount now, and then maybe you'll jump up to 500 or 100, 500, and pretty soon you've got 1,000 op amps to play with, and then every problem looks like it can be solved with an op amp. So good luck and have fun.